Remember what we talked about in the previous lecture?
Unfortunately, I wasn't
Here.
I couldn't attend for about 2 lectures because of immigration.
Okay. So we talk about deterministic finite automata, and today we talk about the finite automaton and formal languages. It is the next topic from the previous on the previous lecture. We talked about deterministic finite automaton and Knus-Morris-Pratt algorithm, and we finish with the pumping lemma, and I don't talk about formal definition of the deterministic and non-deterministic finite automaton, and now we start with it. So about formalization of an NFA. You don't see the recording of the previous lectures.
I was in immigration stuff coming to Russia. I just arrived yesterday.
Okay.
Documentation.
Okay. So we talked that DFA and NFA, it is the graph with the transitions at the edges between vertices. And the vertices, it is the state of the automaton. So remember that vertices equal to states, edges, it is transitions between them. So each edge has the character in it, and we have characters, edges. So it is informal representation of it, and I write in the previous on the previous lecture the points of the axioms of the finite automaton and point what is the difference between these two. But now we talk about formal definition, because formally formally automaton, it is a set of the states. There is alphabet that we use for transitions. For example, in this example, we can use this alphabet. We know what is the initial state. It is usually note with this character. We know what is the finite state. For example, here this is the initial state. It marks with this arrow.
We start from here.
Yeah, we start here. And the final states mark with the double circles. So if we mark it like Q1, and of course in the DFA we can have different finite we can have different finish states. So, for example, we can have such finite finish states of this algorithm. So, it is the set of the finish states, and the main part, it is the transition function of its graph. It's equal to edges in this graph.
Okay.
Yeah. So if we have
Choose the number. Choose the number of vertices.
Q.
Q.
Q. It is the set of vertices. Yeah. It names as the states of the finite automata. So DFA, it is set states in alphabet. Yeah, it is usually finite set. And Q usually is to finite set. Could be 0. Initial state F. Finish states, and the most important here is the transition function. And it is function from Q multiplied alphabet. If we have state and we have one character, we can change our state.
Only once.
And then we read the another character.
For example, we change the state with the finish with another state.
I can change one state to another state with the character. So, for example, if our automaton is here and we read from the string character A, we can change it from Q1 to Q2. So we change it to Q. It is the new state of our machine. So it is transition action. What is NFA? There are different models of NFA, but all of them is equal because if we use NFA to code some languages, do you know what is language of the automaton? Do you know? No? Okay, and for example, for this example, we can say we know what is the sequence of the characters is equal to path from initial state to one of the finished states. For example, I can say that AB, it is the path from Q0 to Q1, yeah? And for example, ABA is 2. But ABAB, it is not path between initial state and finished state. So LA, language of the automaton, it is
related to DFA or
it is the same for DFA and NFA. It is about finite automatons. It is the passes from Q0 one of the finish states.
how do we show that? Like it said, AB, for example.
A what?
How do we show language of a
Okay, yeah. We can show it by the regular expression. Yeah, you can use for LA. Language. We can prove that these languages always is regular languages. And I talk about it in the previous lecture, so I don't want to repeat all the previous lecture. And you see what is it, for example, in the recording. So, of course, we can use, for example, regular expression for all of the languages from this class. For example, for this algorithm, for this automaton, I can say that a regular expression of this language equal to A, B, and then we can repeat A, B, A, B, plus A, B, A, B, A, B. So, for example, this language is equal to this regular expression. Okay, so about formal definition about NFA. There are different models of it, and all the same to DFA, but not transition function delta. For example, we can say that we can use epsilon transitions. And then transition function is equal to our function when we know what is the state of our algorithm. And then we can change it with the epsilon. And about this, about the meaning of it, that we we cannot say that in one moment, we can say that in one moment we in the different positions, in the different states of this automaton. So we can change it to example.
You said that we can have different states at the same time.
Yeah, I say now with the definition because we use suffix links in the not more spread algorithm, and of course it is the epsilon transitions. For example, if we have what AB, and we want to find the substrings of the input line with this word, equal to this word. We can use this finite automaton, but we need to set the suffix links, and I talk about it in the previous lecture too, so see it. And I talk about the suffix links as the connection between the word that we have here and the longest suffix of it that is equal to prefix of this word. So, for example, for this word, we have no suffix equal to the prefix of it, that is not equal to all the characters of this word. So we.
Every single one of them are different. You see that every single one of them are different. Every one of them are different with each other.
They are different, of course. Yeah. So for example, for ABA, we have the suffix A that is equal to this. So we set the suffix link, and of course it is the link with the epsilon character. And here we have such link. So as you see, we can write epsilon symbol here. And for example, if we read string AB, we can say that we in the two states, because we can go from the initial state by A, B, and epsilon. Because epsilon, it is empty character. So you can add any number of empty characters between different characters. But then we, for example, read the A. Oh, I use a different color. So change it to these two states, because we have path from initial state ABA to this state, and we have path from initial state to this state AB epsilon A. And we say that any paths can use epsilon transitions. And of course, you can face with this finite automaton in which there are a lot of epsilon transitions, and you can go through it sequentially too. So, for example, if you have such automaton, you can say that there is path from the initial state to this state equal to BAB. The same as in the edit distance task. Do you remember? When we add different some characters that is empty. BAB from the initial state to this state, not to the finished state, because we can go
can you say that we have also BA?
a path from Q0 to Q2, yes. So if we talk about configuration of the system, for example, in there is configuration. of the Finite automata. And in the DFA, it is equal to state of the automaton and the part of the input string that we haven't already read. State of automaton and so in the NFA, we have not only one state as the configuration of the system. We can have a set of the states, and here is the same. It changes. Where is the set? States. So, for example, here, if we have such input line, we can say that initially we have this configuration, then we read this character and we change it. To this state, then we read next character, and we see that there is epsilon transition. So I write here two states. Then I read A, and I change all of these states with the character A. For example, Q0 changes to Q with index 1, and Q2 change with index Q with index 3. So I said here
This is the configuration of that example.
Yeah, it is the configuration of Finite automaton in the process when we read this string.
And the Q0 is the states of starting point.
Yeah, yeah.
And AB, AAB, AB is the paths that you can have to be the same as the path usually occur.
it is the input line. It can be the any other word.
Can I say that all of them are the same, similar?
No.
Because you have changed the starting point, the order of the characters that
We don't change starting point. We change state of the machine.
Okay.
Because initially we have one of the states, and then we read the character and change it. So further we change this states, and you see that there is no edge with the character A from Q1 and Q3. You see?
Mm-hmm. Yes.
So I can say that we have no state here.
From Q1 to Q3?
Yeah.
We don't have Q3.
So we say that it is error, and this word not in the language of this automaton, for example. But of course, as in the it's about this automaton. About Knut is nearly the same, but you can update this automaton with, for example, with the one suffix link from this point to here, and then we can update it. But yeah, in the Knut automaton, there is other link between these two states with the empty transition. So we can use empty transitions in the common way to build an FA. And it is one of the model. In the other model, we say we can upgrade transitions such that if we have state and we have the character in the input line, we can change the state with the set of the states. For example, for example, this automaton have this automaton has the language equal to words with the A in the third place from the finish point of the what, for example, RA, it is word such that omega n minus 2, I think. Yeah, minus 2. For example, ABB in this language. And we can check it, for example. Can you say some number of characters? Or A, B, okay. A, B. Okay, and I add 1, 8. Okay. And we see that there is A in the third place from the end of this word. So we change the state, for example, with A, and we see that there are two edges that starts in Q0 with character A. It is the edge with character A, and it is the edge with character A. So I change Q0 with these two states, Q0 and Q1. And I read A. B, A, B, A, B, A. Okay. Then I read B, and I see that there is edge from Q0, transition Q0 to Q0 by character B, and from Q1 to Q2. So I set it then I repeat this algorithm. Yeah. So then Q0 with the character A changes to Q0 and Q1, and Q2 changes to Q with index 3. A, B, A, B, A. Then repeat. Okay.
We just remove it and start
Because there is no edge from the Q3. Yeah. And if, for example, we have edge like this, then we can like this. We don't remove it. So finally, we see that there is state from the final set. So we say that this line is in the language of this automaton. Hmm?
If we have A, B, and every edge, can we say that every string consisting of A, B is in our plan?
With the yes, but with the length bigger than 3, bigger or equal to 3. Yeah, of course. And of course, string with the A, comma, and B, it is equal to 2 edges. But of course, we can shortly draw it by this point. So A, B, A, A, B, A, B, A is in the automaton language. So in the books of the automaton theory, you can see such configuration transitions. So don't be afraid of it. Okay. And interestingly, if we use epsilon transitions or we use such function or such transition function, structurally, we cannot get something new because of the statement that if we have non-deterministic finite automaton, then language of it is the regular too. So regular expressions, deterministic finite automaton, non-deterministic finite automaton, it is all about regular languages. It connects with regular languages. We finished the previous lecture with the example that is not regular language. It is slash language. And why this language is not regular? Interestingly, that if we work with the regular expressions or of the class of the languages, we can say that there is we can find something interesting in the structure of this language. For example, we can see at the regular language as the language in the DFA, yeah, that start with the initial state and then go through the graph. And we have some finite states, of course we can have a lot of cycles, yeah. And different characters on the edges. So, what is interesting here? We have language, it is regular, and so we can find deterministic finite automaton such that the language of this automaton equal to L. Due to, you can find algorithms that build such DFA, and we can build the minimal DFA. It is connected with the Myhill wrote theorem. You can find it in the internet, but now we have not a lot of time to talk about it. This theorem is still connected with the structure of the regular languages. It's about equivalency relation on the set of the words that is connected with the language. So we can find A. Yeah. And then we can say that this automaton has finite number of states. And it is very important that if we start with the word that is bigger, such as omega in the language. We know that if omega in the language, we can find the path from the initial state to finished state. But what we can say about this path if omega is bigger than number of states? Then we can say that there is cycle in it. So, informally, I can write it like we have we have prefix as a path to the one of the vertex in the cycle. Then we have cycle, and then we go to the finished state. And it is not trivial cycle, so it is not empty. So there is pumping lemma that says that if we have regular language, there is such natural integer that for all words in the L with length bigger than n. There exists 3 words x, y, z. That is substrings of omega. Such that for all e bigger than 0 to integer number, what is interesting? We can find the path, for example, such path from the initial point to the finish point. Yeah, we can erase this part of the path, or we can repeat this cycle. Y and y.
Can you also do it empty?
Or empty?
Yeah.
Yeah.
Maybe, yeah, instead of while, using the valid.
No, we need to go through this cycle with the subpart of the word y. So, so word xz is 2 in the language. X, y, yz is 2 in the language. And we can repeat this cycle a lot of times. So for all the integer numbers, such words is 2 in the language. And it is about structure of the regular languages. And for example, for the above heads language, we can say that for all we can find words and of course about this dividing, we can write that it is less or equal n, because the finite number of states of the finite automata. I write it with the and y is not empty.
Can I say the same thing about
Hmm?
x? Can I say the same thing about x? As well, it should be always smaller than right?
Xz is smaller than n. Yes, but it's not interesting for us. It's interesting that y can be the end of the words that is very big. If we find omega as the word with the length to n, then if we divide it into 3 parts, x, y, z, such that it's smaller or equal than n, then we can say that y is equal to a in power m. Understandably, yeah, because first n characters is equal to a, and if we know that xy is the prefix that is smaller than n, then we say that y is equal to a in power m.
M is smaller than n.
Hmm?
M is smaller than n. Can be equal.
M bigger than 0.
Smaller than
Smaller than n, yeah, of course. Yeah. Yeah. And then, for example, xz, if you see that as here, I can be equal to 0. Yeah, we can find base xz. And xz not in the language, because it's equal to, and these two numbers is not equal. So n minus m is not equal to n, because in this language we have only words such that firstly we have n a, and then we have n b's. So as a sequence, consequently n is not in the regular class. Okay, and now I think we need break time, and then we start with the we talk about context-free languages, and we talk about other classes of the languages. And because now we talk about regular class, but there is interesting context-free languages, and of course you have already faced with it, because the language of the proper parentheses sequences. Do you remember? slash sequences, and they're in this class.
If you said free language,
A context-free language. I repeated in the after break time, and then we have context-sensitive language, but it is not interesting for a lot of. But it of course connected with the different application of this theory of, and there is very important class that built with the Turing machine. Do you know what is Turing machine? So it is connected with the computational theory a lot, with the P and P classes and other classes. So after break time, we start with it. Organization issues. About code review, unfortunately, I have no time at all. So I hope that Paul and Yesenia find time to talk with you, but I have no, and I see that I have no time until the end of the year, unfortunately too. So it is difficult to find time due to other courses, of course, and other courses of me in the university, because I have 2 exams and other works that I need to do. About exam. This course. Oh. Oh, theoretical tests. Yeah. Oh, yeah. Okay. We can review, but I forget the list. After the end of this lecture, we can talk about if you have time. And if you don't prepare for answering, we can talk about it on the next lecture. In the break time or other. And of course, we have theoretical test about these topics on the next lecture, I think. Yeah, because we end today. We finish with the topic dynamic programming and Finite automatas, and then we start a very short model with the name algorithm that connected with the model arithmetic, and we talk about model arithmetic. Do you have any courses connected with the algebra? And you know what is this set? Z, yeah. You know. What is it? Number of. Yeah. Yeah. And it's about formal. Group, yeah, group theory. And do you have field and ring theory in it? because of course we can talk about some codes that's connected with the we can talk about test format test. Do you know what is it?
Thermal, yeah, yes. Little thermal and thermal test.
When we get the number, we power it into.
Yes.
Okay.
With 0.
I'm not sure if you have that in what is happening.
Okay.
We have increased numbers.
And do you know Rabin-Miller test? I forget, is there T of Fermat in the English? Fermat. Nice. Okay. He was French. Yeah. Okay. And codes. Connected. Do you know what is it? No? Okay. We'll talk about it. And Miller algorithm, codes, and something else. No. I think it will be the final lectures of our course. Okay, and about we talk about pumping lemma. And now we talk about, let's start with the Karasik algorithm. I forget. Karasik, yeah. Karasik algorithm. And remember that what is the Knut-Morris-Pratt algorithm? We have what? We have one word and we want to find substring that is equal to this word. And now we have dictionary. It will be the set of the words. the finite set of the words. Okay. And let's imagine that we have, for example, these words. How we can store this dictionary? As you remember, if we have only one word, we can store it like a graph. And try to increase this picture with the other words. For example, for these words, we can find A, B states, and then we continue and set that is to find final state. With this word, we have A, B. And we add O.
BB, like make it as a loop. A, B, B.
A, B, B, yeah.
It's making a loop on B.
Yes, the first one. Can I make that? No. Oh, no, it won't.
The loop. We can't use loop because loop we can go through loop a lot of times. But we don't want here any words that is not equal to this. For example, words A, B, 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 A is not in the dictionary. So we can't use loop. AA, for example, and B. So it is 3. Finite. Now I redraw it. B. A and B, A, and to build a solution of a heuristic algorithm, we need to do the same as in the Knus-Morris-Pratt algorithm. We need to set suffix links in this graph. For example, we have words A, and the longest suffix here is empty suffix. And of course we talk about suffixes that not equal to the word. and here's 2. Then, for example, for what's AA, yeah, we can draw here this success, because AA has A as a suffix. AB has such suffix, B.
A has AE suffix for AE
The suffix of AA is A,
and AE
is B. It is the longest suffix of this word. Of course, we have empty suffix here, but it is smaller than suffix that is equal to B. Then ABA have the suffix A, because BA is not in the dictionary. So ABB, BB is not in the dictionary, but B in the dictionary, so I found such suffix link. And for this word, BBA is not in the dictionary. BA is not in the tree. We have no node that is equal to BBA. We have no node equal to BA, but we have node equal to A. So we add.
we don't have EA.
We have no B and A. We have no. Oh, no, of course, from the initial point, from the root of this tree. So all of the links with the epsilon transition here, it's the suffix links of this tree. And is it understandable how to implement it as the links? As a you can build class node with the link to other node. For example, yeah. Go back. Okay.
Or we don't have
AAB.
Okay. I thought that we have something like.
We start with this point.
I thought that last one I thought that it's AAB. It's AA and B.
Oh no, it's ABBA. Yeah. Okay.
Fine.
Okay. So for example, node here. Yeah, it is. We have two links to other words. It is the it's a map, I think. Yeah, we can use map children. Map with the types character and node. Yeah. It is understandable why. Because each has character, and by this character we find new nodes. Or maybe a link here in the details of the implementation, of course. Okay, and it's about black links here, yeah, and about and we have only one suffix link from the node. So we add two.
What did you say about node?
About node, we have this node, and we need to understand how to implement it, how to build this tree. We build nodes as the map to other nodes, and suffix link to the longest suffix of this word that is in the tree. So when we when we build this tree, then we can read the input line and go through the Finite Automata, and then if our configuration has state that is the final state, it marks that we find substring that in the dictionary. And then we go through these nodes and find all of the substrings, for example. Then we go this string and write all the final states that we find in this way. Understandable? Do I need to represent an example?
We had some similarities in previous semester, but this would be great if we.
Oh, okay. Oh, you have this algorithm?
Yeah, we remember some stuff, but it would be better if we also.
Oh, better to set the example. Okay. For example, for this automaton, example of the string. For example, if input string ABB ABA, and I need to set the name of the states. I write the numbers here. And we start with number 1. We read A, and we change it to 3. Change it to 4. And you see that 4 is the final state. So we write here the what A, B. We find it. Then we read B. We see that we have transition from this 7, A, B, A. We have transition by A, yeah. 8, B, A, and it is final 2. So we write A, B, B, A. Then we have no transitions by B from 8, and we use suffix link to change it. We change 8 to 3, yeah. B, A. Do we have transition by B? Yeah, 4. For A, yeah. And we write AB2. Find it too. We have 2 substrings equal to AB, here and here. And then we go by A to 6, yeah. And empty was, and it is 2 equal to what A, B, A, yeah, because it is final. And then, before we end our algorithm, we need to go from this state to the initial state by the suffix links 2. So we go from the 6 to 3, from the 3 to 1, because of course, we can find here 2 final states. If, for example, one of the words was the suffix of this word, or this word. We find here words A, B, A. And for example, if we have words B, A in the dictionary, then we find in these places, in these configurations, them. And it is the endpoint of our algorithm. Understandable?
Yes. So we always end in the initial point.
Yeah, we always end with the initial point. Yeah. Because you can see that if we use suffix links, we can go from all of these states to the initial state. For example, here we find this path, this, from this path, and other. So, of course, we end with this configuration. And it is about a heuristic algorithm. And then we talk about other classes. Context. Real languages. Of course, to understand this precisely, it is difficult due to different formal definitions, and we have no time to build it. but we have time to understand what is why we can say that some of the languages context-free languages. For example, context-free languages, it is languages that can build by context-free grammar. And what is the grammar is here? It is number of laws to transform one expression to other expressions. For example, as you remember, imagine all time that if we have such expressions, it is properly processes sequences. So, do you remember, yeah? Such as these sequences. And it is the grammar of this language. So, formally. We have two alphabets. Alphabet of terminants, characters, and I write this gamma of non-terminants symbols. For example, here you can find S as symbols from gamma and two characters equal to parentheses in the alphabet. Non-terminant. Non-terminant. Because these characters can be in the words and these symbols it codes the inner states of the words, but we cannot say that language that We can read two, of course. But after using these laws, we can say we finish with the sequence of the characters from this set. And we can have any symbols from that is non-terminant symbols. And grammar that have that is the set of such diagrams in which A is non-terminant symbol and alpha any word that we can build with these two alphabets. As you see here, we can use only non-terminus symbols or epsilon, or use non-terminants and terminant symbols too. So if we have for example words UAV, we can transform it with this law. We can transform A to alpha, for example. And after some transitions, we get the word, and it is the word from L if all these characters from alphabet of terminant characters. For example, for this word, we can find the way to build it. For example, we start with the S. We start with the S. We transform it by the second law to SS. Then transform first to S in the parentheses. Then I use third. Then I use first, and then I use third. And you see that there is no S here. So I say that it's a word from the language that we built by this context-free grammar. Of course, this grammar is context-free. In this example, we have these two alphabets. But in your task, you need to understand what is the alphabets by yourself. Yeah.
You said with alphabets of terminant characters, the characters can be in the word. For example, S can be in the word, or the parentheses.
You can use S in the inner states of your words. But finally, you have word without s. So it is context-free grammar. And there are some other grammars as context-sensitive grammars, or in the common way, you can write here alpha and here write beta. That in the that is the word from this set. In the common, yeah.
For example, this here S is non-terminal symbol and
Yeah.
parentheses.
Or we can say that any non-terminal symbol equal to substring of the words. You can imagine it like a tree too. Because, for example, initially we have S, yeah?
Yes.
Then we transform it to two nodes, S, S, yeah? Then we transform first to very understandable, yeah? And then we transform it to and these two epsilon and epsilon. And what is the word that we print? It is the leaves of this tree. And of course, you can say that S is equal to subtree. For example, this S, it is this subtree, and it is equal to substring of this word. So it is about how to imagine what is the non-terminal non-terminal characters. So you can understand why if we use these three by the definition of proper parsed sequences, it is understandable why these three laws give us only these sequences. So, what is interesting? For example, interesting that regular languages always context-free languages. And of course, it is very understandable because, for example, if we have determine Finite automaton, for example, this, yeah? We can say that each state is equal to non-terminal character. And then we replace edges with the laws in the grammar. We can replace A with the character A. C. C. B. AA, yeah. And of course, due to the finished states, we can transform B to epsilon 2. So it is the context-free grammar that give us this language or this automata. So all the regular languages is always context-free languages. So I can write here this diagram. Yeah, that context-free languages contains regular languages, and further applications of it. Where you can find automatas. For example, of course, you can find in the theory of complexity classes. As I understand, you know what is it? P classes and P classes. You have introduction to it, yeah? P and P, no. Polynomial computational classes. No, it is non-deterministic polynomial computational class. For example, P space. It's true. Okay, and I think you have other courses about it. Maybe on the third term, fourth.
What is it called again?
What is the classes? It is classes of languages that you can solve using some resources. For example, this class is equal to polynomial tasks. For example, we talk about only polynomial task here because we have a lot of resources, and we need to solve the examples with billions of input data. So we need to use such polynomials that has asymptotically very small time complexity. Do you remember time complexity? Yeah.
Yes.
Yeah. And for example, if we can upgrade these restraints to, for example, exponential restraints. Yeah. If we have exponential restraints, it is XP class, and we have a lot of other restraints that give us different classes. It is interesting that then you can face with cryptography. Do you know what is it? Okay. And of course, interesting that, for example, do you know sites random points.org? Random. No? Okay. And if you need to, or do you code the task to give random numbers from the, for example, real numbers? some random real numbers.
Generating random numbers.
Yeah.
Yes, we have found it.
Okay. So interesting that usually if you have
Yeah. By the way, in previous semester of number theory, we had cryptography, and one of the ways was generating random number named local key, if I'm not mistaken, and public.
Yeah. RSA, for example. You know what is RSA?
Yeah. Second, we had one other, we had two other encryptions, RSA, and it was 4-letter, if I'm not mistaken.
And do you know what is one-way weak function? No?
One-way weak?
Weak, yeah. Because do you know that, for example, if you have function, you can find that is bijective. You can find such function. What is the name of this function?
Inverse.
Inverse function. Yeah. But do you understand how to go from function to inverse function? How to find it? Of course, if, for example, we have restraints for this function, if we know that, for example, this set is finite and very small, we can build it by hands. Yeah. For example, if it is linear, we can find linear inverse function as in the linear algebra. But in the common way, if we have very complicated set, it is very computational difficult task to find inverse function. And so it is very important in cryptography to find such functions. And it is connected with the finite automata too. Also, in the application of this informatic theory, I think it is useful in the architecture. Because there are some of the processes in the computer that use finite automatas, and for example, lexical analyzers too. Do you understand what is lexical analyzers? Do you know what is it?
I understand, but I have some difficulties to understand.
You know that if you write some code, you can compute it, and then if you forget to write parentheses, your program says that you have warning or you have error, because in the computation there is lexical analyzers that find, for example, here, if we find open bracket, we need to find close bracket. Yeah. So if we don't find, we can say, oh, you have no properly parentheses seconds. So lexical analyzers do something similar to this explanation. And for example, control theory was economic. For example, about control theory, for example, yeah, if you have some process and you have different states, for example, in the industry programming, you face with the process names as the circle of the realization task. I don't know how it in the English, but for example, you have some states of your group. Yeah. For example, initially you don't know how to solve your task. You discuss with your colleagues and find the ways to solve it. You implement it, you optimize it, and you make a product by your realization, and then you cycle it. Yeah, so there is some theory about this process, how to make comfort working of your group. And about economic theory, of course, there are some economic processes that transforms by this transformation to because there are some economic systems that transforms discretely. So you can say that state of your economic system is the state of finite automaton, and then use it to explain how your system changes. So yeah.
How did you connect how did you connect it to economic theory?
It is connected with control theory. I think there are different tasks where you can imagine such diagram, and then your process changes by this diagram. For example, yeah.
Can you explain something after this graph? And I didn't understand that one, how they were connected. You used automaton for it. I didn't did you understand my question?
Oh,
The thing you explained after this part.
how to expand this?
No. Okay.
I think it's very abstract explanation, of course, about application of the automatons, but I think that here in the automaton you have two main parts: edges, vertices. Yeah, it is equal to states and transitions from the states. And in all processes where you have states and transitions between them, you can say that it is finite automaton. So in the economic, you can find two state of the system, and then this state can change, and these transitions is equal to edges in your Finite automaton. And for example, of course, in the in the biology there are two processes that we can imagine as the Finite automaton. Of course, it is interesting as the picture. I think that we can see at this picture, we can see at the Finite automaton and find something interesting about our process. Yeah, so I think that's all about applications. Of course, the most important applications is in the theory of complexity classes and these two cases. In the other science directions, it is still applicable, but not so necessary as in the math applications or in the theoretical programming. So it is all about finite automatas. And next time we start the final. No, next time we have, I think, theoretical test about dynamic programming and finite automatas. And then in 2 weeks we start with the final module. That's all.